Hey, good morning. It is March 17th, Monday. Network cabling, ELEC 1013, Fanshawe College. Alright, so today we're going to start the first of the two lessons that we're going to get on fiber optics. And the fiber optics number one lesson is the basics of operation. The second part this week we're going to get is going to be practical applications. All right. Fiber optic cables or optical fibers are links, communication links through which signal travels in the form of light, or more precisely in the form of light pulses. So the signal that travels through the optical fiber is not electric signal, it is a light signal. Which first thing that comes to my mind when I say that is that because it's not electrical signal, then this cable is not susceptible to the outside outside factors such as electromagnetic interference. So if there is a lightning storm outside, it can go in storming and lightning all night long, and you're not going to hear anything as interference because it's light, not electric signal. So the signal through the fiber optic is quite clean. It can travel further distances. Now, as far as the spelling of fiber, I'm still trying to decide which one we're supposed to use. However, you're going to notice both spellings in all kinds of literature when it comes to this topic, and sometimes you're going to see F-I-B-E-R, or sometimes you're going to see F-I-B-R-E. Both ways of spelling are correct, and different companies assume different convention as far as spelling of the optical fiber or the fiber optics. All right, what do we see here? It's a popular type of object, what we popularly call a rainbow. What is a rainbow? First of all, how can we see it, or what conditions have to be met for the rainbow to exist? Well, first thing is that it has to rain, so there has to be something in the air other than just air. And second condition is that you have to see the sun. So if it's raining and if you can see the sun at the same time, for sure you can count on it that it's going to be a rainbow. Where do you look for it? Well, you look into the sun. Well, don't look directly into the sun, but face the sun and just turn around. The rainbow is going to be behind you. What is it? It's basically a light that is split into different frequencies or different colors, because the light that we recognize, different frequencies, we humans see the difference between different light frequencies as colors. Same as we see the differences between different audio frequencies, the frequencies that we can hear, we can receive those differences or the different frequencies as different tones. You could have a low tone, you could have a high tone. That's how you distinguish the different frequencies with the sound waves. And with light waves, we can see colors. Now, is there anything beyond the violet? Yes, there is. Is there anything beyond the red? Yes, there is. It's just that we humans are able to see things, colors from here to here. Certain animals can see a little bit further this way. Certain animals can see it a little bit further that way. Over here would be, example would be dogs, deer, and animals like that. And over here, birds would be turkeys, hawks, eagles, and similar animals. You can see a little bit past or frequencies higher than the violet. They can see different. So the way we see this not necessarily is going to be the way some kind of an animal sees the same thing. But we're used to seeing it this way, so we're just going to keep looking at it like that. All right, how is the rainbow happening? Well, here we have something that's popularly called as a prism. We have different medium here, and we have a different medium here. Let's say here is the medium that is this that makes up this well, this area right here is glass. And let's say that the medium on this side is air. And over here where the air meets the glass, that line, we're going to call that an interface. So when the light beam, white light beam, because white is actually not a color, white is presence of all colors. And same as black is not a color, black is an absence of light. So when we have a white light passing through this prism here, it meets the interface. Let's see what happens. If the light beam was hitting the interface at the right angle, passing the interface, the light would still be white. The colors would not be split. It's just the light would travel slightly slower in glass than it would travel in air. When we have the angle of incidence high enough or low enough, well, it's going to be high, because if this is the zero angle, then we move it, so we're looking at this angle of incidence. If it's high enough but not too high, then the light is going to enter the prism. You should probably remember this from your grade 11 or grade 12 physics. So now so far there's nothing new for most of us, unless we were sleeping through that lesson, or absent otherwise. Then what happens is that the light begins to split, because different frequencies that are actually present in the white light are going to interact with the other medium, which has something as index of refraction or refractive index or index of refraction higher than the air, then something interesting is going to happen if it's going to be under an angle. Different frequencies are going to react with the other medium in a different way, are going to be affected in a different way. As you can tell here, the violet waves are bending that much. And if you go towards the red area, the frequencies are still affected, but not as much as the violet waves. Which means if you were to use light as a signal, as a form of energy, or form of a signal, in a glass, which one would you decide to use for a transmission? Well, it's an online class. So I'm going to answer that. Yeah, there you go, Clark. Light reflects in the moisture or water. Yeah, it reflects, but in this case here, it refracts. There's a difference between reflection and refraction. So the blue light or the violet light waves are higher frequencies, you can see that. And if you go towards red, the frequencies values are becoming less, making the wavelength longer. Right? And as you can tell, that the violet waves bend more than the red ones, which means the red ones are less affected. So it just makes sense that if we want to have a signal that is not affected as much, or affected the least, which means slowed down the least, and generally affected as maybe attenuated the least, it passes easier through the medium towards the red frequencies or the red colors. And that's why the light that passes through the fiber optics is actually infrared, which is below red, so lower frequencies, because over here would be ultraviolet, and this is infrared. So we humans will not see the signal that is passing, but the signal is still there. The equipment, it's not important that we see the light. What's important is the transmitting equipment is able to transmit those frequencies that we don't see anymore, but it's still considered light. And what's important, that whatever receives, the receiver of the signal is able to receive that, same as we don't need to see the radio waves in order to listen to the music on the radio. All right, as far as the calculations, let's see here. The wavelength is represented by the Greek letter lambda, and it looks like this. And the wavelength is, the unit of the wavelength is meters. Okay. The frequency is represented by the letter that looks like a V, but it's a Greek letter that is called nu. Just like the new car, but it's like a little bit of like a silent I, but it's like nu. And it looks like just our V. And the units, the frequency, is whatevers per second. So if we're having the meters wavelengths per second, so the frequency is going to be meters per second, or vibration, no, not meters, vibrations per second, or occurrences per second. So that's why we didn't put anything here. The speed of light, well, it's represented with the letter that looks like a letter C, and I'm just going to say that this is the letter that represents speed of light, is represented by meters per second. So that's the unit. Light travels very, very fast. Speed of light in a vacuum is considered to be this number here, 299792458 meters per second. So 299,792,458 meters per second, which sometimes is rounded up in certain calculations to 300,000 kilometers per second. Or simplified, the speed of light is 3 times 10 to the 8th meters per second. I would recommend that you would watch these two videos at home once you download this. Or here they're basically the references. So that's, yeah, there's a YouTube video, and there's some another reference to this topic. Sometimes there is confusion because when you have the frequency, you can reverse that, and you're going to get the period. And if we have a period, you can reverse that, and you're going to have the frequency. So that would be that. But this is not how we're going to calculate the speed of light versus frequency and wavelength. Here's the formula here. Frequency equals the speed over the wavelength. So by the same token, if we want to have the wavelength, what do we have to do just to derive wavelength? Well, wavelength, if we divide it by speed, so speed and speed are going to cancel, we're going to have wavelength left. But if you divide it by speed, you're going to have that here. Wavelength equals, so 1 over wavelength and that, so we have to reverse. So wavelength equals speed over the frequency. And here's the reference triangle here. If you cover, so speed equals frequency times wavelength. Wavelength equals speed over the frequency. And frequency is called speed over wavelength. Okay. That's how we calculate. In order to get the numbers we're going to see over here, or the next slide. Here is the visible light within the all frequency spectrum. Here we have gamma rays, extremely high frequencies, then we get a little bit lower, we get X-rays, and then we're going to experience ultraviolet, which is over here. So these are high frequencies, these are lower frequencies. And over here, further there, you're going to see, somewhere here, you're going to see the audio. Everything vibrates, depending on how it vibrates with what frequencies. We're going to classify the frequencies in a different way because they behave different way and have slightly different properties, and they could be used and detected in a different way. So over here will be sound frequencies. We're going to go move up, and finally we're going to hit the radio frequencies or electromagnetic waves that are being used to transmit through the radio frequencies. And on this side, we're going to hit infrared, so below red. These are lower frequencies. And over here is the visible light, right here, that part here. So this is the light that we can see as humans, and below those frequencies, we can't, but they're still there. It's considered a light. And over here we can see, but still considered light. Now, remember when we said that the red frequencies are affected less? Well, it just makes sense that if we choose the frequencies in that area, excuse me, then the frequencies are going to be affected less. Then maybe we can transmit the signal further with less distortion. Makes sense. So over here, which is the light below what we can see, that's where the optical fiber transmissions are happening. Now, the typical visible light to us humans, excuse me, is around 400 to about 750. And what's that nm? That stands for nanometers. It just so happens that when we're talking about the frequencies that we can detect with our ears, or frequencies that are with radio, for example, we have tendencies to express them in the frequency unit, which is hertz, which is basically Hz. That's the famous Hz, so that's hertz. And it is after the last name of the person who introduced humanity to the idea of frequencies. And just as, one important thing that I'm going to tell you, when you're counting hertz, you're going to have 500 hertz, you're going to have 100 hertz, you're going to have 50 hertz, 20 hertz, 5 hertz, 2 hertz, and we're going to have 1 hertz. Not 1 hertz, because hertz is not a quantity of how many hertz. Not like that. The hertz is the last name. So there's 1 hertz, not 1 hertz, as sometimes people have tendencies to pronounce. Now, where are we here? Fiber optic communication typical wavelengths would be, now, the light frequencies that are being used, we are not expressing that in hertz. We are flipping them around a little bit, and we are expressing them in wavelengths. The same thing, certain frequency is going to have a certain wavelength. So we can express frequencies in frequencies, waves in frequencies, or we can express waves in their wavelengths. And it just so happens when we talk about light, we have a tendency to express the light frequencies in reference to their wavelengths. So typical fiber optic communication frequencies are 780 nanometers, so somewhere here, 700, 800, somewhere here. 850 nanometers, somewhere here. 1310 nanometers, so somewhere here. And 1550 nanometers, which will be somewhere here. Why those? We're going to talk about that next time we see each other. It has something to do with the water absorption. These are for the most part, the most efficient wavelengths along the invisible to us area here that the light travels in an efficient way. If we choose any frequencies between that, chances are that the signal is not going to get through to the other side of the fiber optic link. I'm not going to get into the details of that right now. We're going to get into the details second time we see each other. Let's keep going. Here are the frequencies and here are the colors, because light differences in the frequencies we express in colors. And here would be the wavelengths and here would be the frequencies. So the wavelengths usually we'll be expressing that, not usually, but we just are expressing that in nanometers, because that's how long those frequencies are, how long the periods are of those frequencies. And the frequency values would be expressed in terahertz. You have to apply that formula that I gave you in order to convert these to those, not just reciprocating it, like putting 1 over top. So 1 over 668 is not going to give you 380. It's going to be a little bit. You have to apply that speed of light, frequency, wavelength formula that I gave you, and it's just going to then you're going to make sense out of this table here. The frequencies, wavelengths over the frequencies of the frequencies. All right. Then let's get the idea of refraction, reflection, index of refraction, and the idea of total internal reflection. A lot of mouthful here. Tongue breaker. Refraction, reflection, index of refraction, total internal. Okay, I can say it fast. Can you? And there's also going to be a link to a video that is going to give you a little bit more detail on that. But again, I'm going to ask you to watch that at home. Well, you're at home now, but you know what I mean. Refraction. Light refraction through glass and water. Let's say this here, or let's say this right here. Here is air all around us. It surrounds us. We are surrounded by air. And the area where the air meets glass, or the air meets water, this is the interface, and this is called interface. Now, the line that is perpendicular to the interface, we are going to call that the normal. The normal. The normal what? No, just the normal. Treat it as an object. Or subject. No, object. Noun. The normal. It's the line that is perpendicular to, at the right angle to the interface. And the angle that is deviated from the normal, under which the light hits the interface, we're going to call it an angle of incidence. All right. Notice that remember when we shine the light, we have a light beam or light mode, or otherwise beam. So let's get used to the word mode as a light beam. If it's a single light mode, single light beam, hits the interface under a certain angle and the environment changes, then the light mode or the beam is going to get affected. Angle of incidence and angle of refraction is going to be different. Now, this is a dense object, and this object as air is a little bit less than dense. It's a little bit more dense, denser than the vacuum, which is the total absence of anything and everything, or total absence of matter. Then, of course, if it's something denser, then it's going to affect the light, which is going to slow it down. Normally, if it passed through, it would continue this way, right? Like this here. But when it's slowed down, it bends towards the normal. So the index of refraction is going to be slightly less, or the angle of refraction, than the angle of incidence. But we have the same angle of incidence here, and in different type of medium, the light beam is going to bend away from the normal, or it's going to bend towards the normal, a little bit less. It's going to be closer to the original path of travel, or the direction of travel, or the original path. So different mediums are going to affect the light in a different way, which we can say that the different mediums have different index of refraction, not a reflection. Refraction happens when the light penetrates the interface, enters the other medium, and it's affected. So it's refracted. The direction of it is being changed. Now, when the light travels to the other interface, so it leaves the medium, it goes back to the same angle that it was. See that? Here and here. Reflection would be like a bounce off. If the light reflected from the interface, it would bounce off the interface and it would just go that way. That would be reflection, and penetrating it and going through the medium is called refraction. Now, when it happens to the signal travel inside the optical fibers, which one do we want to accomplish? Do we want a reflection, or do we want refraction to occur? Well, let's take a look at further slides. So the reason why the light is being affected in a different way is because this medium here, comparing to that medium, or vice versa, those two mediums have something that's called different. They have index of refraction, or refractive index, or index of refraction is the proper way of saying it. And the index of refraction tells us how much that medium is going to slow down the light. Is it going to slow down the light more? Or is it going to slow down the light less? Let's see. Maybe we can come back to this slide here. The difference between refraction and reflection. Here we have air, and here we have, well, aqueous medium, which you can say water. Now, in the water, light is going to travel slower. In the air, the light is going to travel faster. So here's one medium, here's the other medium. Now we are shooting the light the other way, out of the water, towards the interface, where on the other side of the interface there is air. So here is the interface, which means the line that separates one medium from the other. All right, so here's the normal. Here's the angle of incidence from the normal, because this is also normal because it's parallel to that. So let's say here's the light source, so there are going to be normal here perpendicular to the interface. Now, if we shoot that light straight, it's just going to continue in a straight line, which we shoot it along with the same angle as the normal, which would be our zero angle as a reference. We choose that to be the zero. If we start increasing the angle of incidence, then the light is going to get refracted, which means it's still going to penetrate the interface and go on the other side. And it's going to change the angle a little bit, change the angle a little bit, change the angle a little bit, until we reach something that is called a critical angle. And a critical angle is when the light doesn't go either way. It doesn't penetrate the interface and travels through it, and it does not bounce off the interface, and it doesn't, which means it doesn't reflect. It's called a critical angle. And then if we keep increasing the angle of incidence, at some point we're going to pass the critical angle. So here is the critical angle here, same as here. Those two angles are equal. And we're going to accomplish something that is called a reflection. Still, can we say which we want to accomplish, reflection or refraction, when transmitting signal? Because that's the whole objective of this whole class, of this whole lesson. It's the way how we can harness the light in order to work for us, the way it travels through different types of mediums. So how we can use the physics of what happens to our advantage. In our case, to what we want to accomplish is we want to accomplish the traveling of the signal through the whatever medium. And the index of refraction is represented with the letter N. See that here? Now, here is the water, and let's say we're going to have the index of refraction 2 of medium number 2, which is water in our case. And here is the medium number 1. So here's the index of refraction of the medium number 1. Now you can see that water has greater index of refraction than the air. Well, it makes sense. Water affects, because what does the index of refraction tell us? The index of refraction is telling us how much it is going to affect the light, how much is going to change its path, how much it is going to disturb it. So water is going to slow down the light more than the air. The air is going to slow down the light just a tiny bit comparing to the vacuum, because vacuum is our reference. So because the water is going to affect the light travel, or the light way of traveling more, that means that the index of refraction of this index number, or the medium number 2 that we just numbered them randomly, the index of refraction of water is greater than the index of refraction of the air. That means in the water the light is affected more, and in the air the light is not affected as much, which means it can pass through easier than through water. And we're talking about the angle. Here's the angle of incidence, angle of refraction. Here's the normal. If you keep increasing the angle of incidence, at some point you're going to keep increasing the angle of refraction until you reach the critical angle, and you pass the critical angle, keep going, then you're going to start reflecting the wave, reflecting the mode, or reflecting the beam. Beam, mode. Okay, beam is mode. Mode is beam. Remember that. And then we're going to start accomplishing something that's called reflection. Now let's see that here. Index of refraction. That's the letter N, equals speed of light in a vacuum and the velocity of the light of the medium, of the light in the medium. Okay, what does that tell us? Here is our reference. That's the speed of light. And this is the speed of light in whatever the medium we have. So if we are pushing the light through water, the index of refraction is going to be speed of light over the speed of the light in the water. And since anything other than vacuum is going to slow the light down, so this speed was always going to be slower than the speed in the vacuum, than the speed of light in the vacuum. Huh? So the most you can get as an index is going to be 1. because if we pass the light from vacuum, from vacuum to vacuum, we're going to have the index 1. All right, now when we pass through different ones in different mediums, that index is always going to be greater than 1. See that? The more the light is being slowed down, the greater the refractive index is going to be. Yeah. So it's going to be the lowest is going to be 1. Yeah. Yeah, there you go. Index of refraction. This speed in the medium will always going to be slower than the speed of light in the vacuum. So if the velocity if the velocity in the medium decreases, so means if the light travels slower through the medium, which means the medium is affecting the light more, then it has greater index of refraction. Materials with higher index of refraction slow down the light more. And so, indexes of refraction of different materials. Vacuum has the index of refraction of 1, and that's as low as you can get. The index of refraction of the air, it's almost like vacuum. But look, there is a bit of, something is beginning to happen here. The index of refraction of the air is 1.000277. All right. Now, the light is going to travel slower in water because water has a higher index of refraction. The ice has even higher index of refraction, so it's going to slow down the light more. The glass is roughly about 1.5, so it's going to slow down the light even more. And here's the diamond, slows down the light even more. Well, we're going to concentrate on this medium right here. Go back to this slide here for a sec. Let's say we want to transmit the light through the water. What will we have to do? We would have to surround the water by air, right? So if we could just kind of do the Jedi Force and make like invisible pipeline. If we could make a round pipe out of the water here, and if we could make another round pipe that surrounds the smaller pipe, then we could contain the light beam. So let's say this one here also, it's cut through and just see the two-dimensional view. So here is the air, here's the water, here's the air. Well, and we want to keep it in. So we want to make sure that we accomplish the angle of incidence high enough that the light stays reflected within here, the water, and doesn't leave our pipeline. So we don't want the light to refract. We want the light to reflect. Okay? So in this case, if we shoot the signal, it's going to go bounce off and stay within, and then bounce off and stay within, and bounce off. It's just going to continue bouncing off until it gets to the other end. And we can catch the beam or catch the mode and read the signal. Okay, let's go back a little bit here again. Which means, look at this, the light in water travels slower and the light in the air travels faster. Keep that in mind. Keep that in your mind. It's just like having a paved road, and if that road, paved road with a pavement, asphalt or whatnot, concrete maybe, and if we're driving a car, or let's say we could roll a billiard ball, it's going to roll, and if it hits the other material, if it were made out of ice, which would be slippery, it would just bounce off that slippery surface and keep going there. If it was the other way, if we rolled the ball here, it would roll faster, but as soon as it hits that hard surface, it's going to be slowed down by it, and it's going to be pulled towards it. I think I got text from Mr. Riekers here. It says, I'm teaching online today. Can you quick tell the students? So stay online. When we're done, you're going to get Mr. Riekers here. I think that's what it means. Mr. Riekers, are you here? Okay. So whatever that means, maybe Mr. Riekers is going to step in after I'm done here. Maybe soon. All right. Keep that in mind, what I just said. Total internal reflection. Well, here's the source of the light, and here is our optical fiber link. Here is glass, and here is glass, but those two glasses are slightly different. In which way? Well, in here is the core, and around the core is something that's called a cladding or surrounding, embracing, hugging. So the core is surrounded by the cladding, is cladded by the cladding. Now, this core and the cladding are both made out of glass. They're made out of highly, highly, highly pure glass. How pure glass? Well, you can transmit the light from here to Toronto, no, from here to Kitchener, which would be about 100 kilometers. And it can still pass through. Now, we want this core here to be slightly doped with whatever materials that we can dope it with to make it slightly impure. And the cladding, we're going to also dope, but in a different proportions, so the cladding is not as dirty, quote unquote, as the core. The core is made a little bit more impure than the cladding. Cladding is cleaner. If we shoot down the light in a straight line, the light in the cladding would travel faster than the light in the core. I know there is a tendency of thinking that the light should travel faster in the core than in the cladding. No, it's actually the other way. If you make the light travel faster in the cladding, then the cladding is going to look slippery, quote unquote, again, slippery, in comparison to what's in the core. Which means that if you were able to shrink yourself and have the abilities to penetrate surfaces, and if you walked into that core, you would be surrounded by a round tubular mirror. It will be just one big tubular mirror, which means basically the interface between the core and the cladding would act as a mirror, because this is made slightly impure, and this is made also impure, but not as much. So the light would bounce off the slippery surface. Each mode, each beam would bounce off at a different angle. So each beam would take slightly different time to get to the end. There would be some modes or beams that travel in a straight line, so they will cover the least amount of distance, so they will get to the destination faster, quicker. Then the beams or the modes that would reflect under an angle, they take, they will have to cover more distance because of the reflection. So that's why sometimes we have something of that's called a graded index, multi-mode fiber, multi-mode, multi-beam. Beam under a different angle is called a mode. So the straight beam or straight mode is going to be called, well, its own mode, and all the angles in between. How many of those modes are there from the source? How many modes? Well, infinite number of modes. We just drew some, because the light would be dispersing angled in a different angles here. So that is something that's called a multi-mode fiber. And again, core has a higher refractive index, which slows down the light more than the cladding would, and so on. The light travels slower in the core than it would in the cladding. In order to accomplish what? In order to accomplish total internal reflection to contain the light. All the beams that are inside the core are reflecting. Thus, we are able to transmit the signal, contain it within the core, and carry it to the other side. Thanks to total internal reflection, we are able to accomplish a signal transmission. Now, we distinguish multi-mode fiber and a single mode fiber. Notice that the core in a single mode fiber is very, very narrow, extremely narrow. So the light that travels is very narrow, pretty much single mode, single beam. And it is ideally not reflecting off any walls because this core is so narrow. But in reality, it just would kind of wave just a little bit, but not as much as the multi-mode. The diameters, the outside diameters are the same in both cases. The core in the multi-mode is wider, and the source would be LED, and the core is narrower in the multi-mode fiber, and the source would be a laser. So more expensive to produce and accomplish, less expensive to produce and accomplish. Light can travel quite a bit more further. It can travel further distances and still keep the integrity of the signal. But it costs more money. But if you don't have so much distance to cover, less distance, then you can use multimode fiber, less expensive equipment, but the signal is going to be not as sharp on the other end. But if it's distant, the distance is short enough, and you slow down the transmission enough, then you can accomplish quite a bit as well. How far? Well, with the Ethernet cable, we can travel 300 feet at the most. Well, with the asterisks, note that some time ago, recently, well, relatively recently, this is 2025 now, and I don't remember the year, but it was just not too long ago, there was another cable that was called Game Changer. The name of the cable is actually Game Changer. The Ethernet can travel up to 1,000 feet, which is about 300 meters, 1/3 of a kilometer. Well, with that here, the normal transmission distance would be 3 kilometers, and that's considered short distance as far as fiber optics is concerned. Fiber optics are concerned. Over with a single mode, we can transmit the light 100 kilometers. Well, still more than 1,000 feet, or still more than 300 feet. The diameters of the cladding in both cases, are the same for the most part, and they're 125 microns. 125 microns, which means micrometers, which means 1/1,000,000th of a meter. And the current way things are being produced in 2025 or so, the size of the core in the multi-mode is about 50 microns. And the typical size is anywhere from 5 to 10 microns, typically 9 microns for the single mode. So if you just look at the single strand of fiber, you can't tell unless we take it into a microscope, but then you should not be doing that if you don't know where the other end is. So if you hold a 3-foot piece of fiber optic in your hand, you know that the other end is not connected to anything. Yes, you can look straight into it because, it's just nothing there. But if you don't know where the other end is, never, ever, ever, never look straight into the fiber, because you won't see the light, but the light and its energy from a laser is still there, and it can actually burn the back of your eye. It can burn your retina, and you're going to see a dark spot everywhere you look for the rest of your life. If you're lucky. If you're not so lucky, you can actually go blind on that eye. So multi-mode, single mode. Optical multi-mode 2, optical multimode 3, optical multimode 4, optical multimode number 1. It used to be 62.5 microns, the core, and of course 125 microns. That's the older version of fiber optics multimode. Now all of them are produced 50 microns. 50 microns cable you can get off the shelf on any distributor. If you want to have 62.5, the older version, you're going to have to wait maybe a week because it would be a special order for that. Why would you want to? Because, well, some of the old installations are still intact, and the equipment that is there is, well, made for 62.5, because fiber doesn't corrode. So some of the existing still optical fibers are, from 1970s, still okay because they don't corrode. So typically that's the new standard, 50 microns multimode. Now OM1, which is optical multimode 1, 2, 3, and 4, it's the order that they were made. So OM1 was made first. Then the engineers would work on the technology and come up with something better, and they would call it OM2. Then they would come up with something kind of a little bit better, and OM3. So that's how it goes. Now, as far as single mode, typically 9 microns, but it can go as long as 5 microns as far as the core. So that will be the differences. The anatomy of a typical optical fiber will be, here's the core. Right, so let's say this is 8 microns or 9 microns. You can tell that this is a single mode fiber. And it's cladded or surrounded by cladding, typically 125 microns. And that is the essence of it. Everything else that covers that is for protection. So you will have a buffer, different jacket, surrounded by whatnot as you need. So obviously you will not have to protect a fiber optic that is being laid in the cable tray above the ceiling somewhere and carefully placed so nothing presses on it, nothing touches it too much, and it's nicely laid. You don't have to protect it as much as you would have to protect the essence of our transmission here if you run that under the ocean between the continents, so the sharks don't bite through it and so on. So you have to have more protection. So and there's anything in between. Multi-mode and single mode. Core and cladding size, so 50 by 125, 9 by 125. Core versus cladding, core versus cladding. Wavelengths, typical wavelengths that are being used for the most part, multi-mode, 850 nanometers, 13 nanometers, and there will be LED source, LED source, sorry, LED. And then for the single mode, typical wavelengths that are being used would be 1310, 1550 nanometers, and the source would be laser. Bandwidth, how high frequency can you pass through it, so, and the cable is able to transmit that to the other end, and so it's still recognizable and not aliased, which means distorted in a certain way. The frequency, right? So up to 4 gigahertz for the multi-mode. Now the bandwidth, we're talking roughly up to, because I don't think the equipment has been invented to actually choke single mode. So we're kind of agreeing to up to 100,000 gigahertz. That's a lot of hertz. Quite high frequency. a lot of information. So see that there are differences between the single mode and multi-mode. Distances typically under 2 kilometers, although some sources will tell you 3 or 4 kilometers. And this one here, typically, well, that's a very sneaky way of saying it. Typically over 2 kilometers, and some sources will tell you up to 30. Some sources will tell you up to 70. Some sources will tell you up to 100 kilometers. That depends on what equipment was available for testing at that time and which year the report was produced. Yes, but there are cables that can transmit the light pulses 100 kilometers. That means without the need of reamplification. Benefits, excuse me. Well, it's less immune to contamination, whatever that means here. Less expensive, low cost sources. So it's cheaper to have multimode. And if you're connecting closets, communications closets within the building, you don't need single mode. Although you might want to. Not gonna hurt, but it's gonna cost you more. Well, the benefits of versus the single mode, it's lower loss of the signal, high signal quality, and high bandwidth. Applications, well, for the multimode data centers with 10 gig, 40 gig, 100 gig speed, Ethernet protocols, and so on. Here, multi-channel audio digital interface, which would be that fiber optic cord that is included in your stereo, somewhere in the bag that contains the manual. So between the communications closets and short distance applications such as less than a kilometer within the building. Now here, long haul networks, outside broadcast, ENG, electronic news gathering, sporting and live events, so TV and so on. That's plus all the internet, telephone, and whatever communications that you need in a house or facility or commercial building, it can be transmitted on very minimal number of optical fiber, which is single mode. Here's some helpful links that I would encourage you to watch. And this was the last slide. Sorry. Yes, well, we went a little bit over the time, but now we're up to date. So you can catch whoever had to go to the other class. You can catch that as always on YouTube, because I'm posting it right away. Other references that I have to include, and that is it for today. Thank you for your attention, and I will see you when I see you.